So what I'm going to do is have a little bit of a talk about what we do as Face to Southland, and Tom didn't know anything about it. I'm guessing many of you don't either. So let's get into it. But first of all, a message from our sponsors. I mean, we've got to acknowledge all the work Carlos has done, and I'm really disappointed he's not here today. But just to calibrate myself, they would recognise that. Yep. Sputnik, yeah, and just to get a calibration of the ages, a few grey hairs, but not many. I think I've got the least and the most. When did it go up? When was it launched? 1957? Yeah, 4th of October, yeah. So you could argue that was the most important in the space, was the Soviets getting to space and people going around the Earth and spotting the moon. And perhaps for different reasons than we might expect. Is that still working? The problem was that the West thought that the Soviets were a bunch of peasants and they couldn't imagine that they could. But also they realised that maybe there was something inside Sputnik that might be radioactive that could deorbit somewhere in the West, and you would need bombers when you've got something like this. So the good news was that people like me got an awful lot of education, what we now call STEM, science, technology, education, engineering and mathematics. And I wove the... I benefited this all the way through the 60s and 70s because it was something rather that the West really wanted to put into it. And hey, maybe it was good. Anyone recognise this picture? Oh, no, I know you know it. Yeah. Yeah, but the important part of it. Okay, so that was taken, a photograph, it's called Earthrise. It was taken by William Anders on Christmas Eve, 1968. And so it was Apollo 10, so it was the precursor mission to Neil Armstrong and Apollo 11 going to the moon in 1969. You could argue that that the whole Apollo program, this was the best possible outcome. Landing on the moon was great, but this photo was the first time that human beings had got out of Earth orbit, or Earth's gravitational pull, and got onto another system. And for the first time they could see the Earth in its entirety. And the thing was, it wasn't very big. And all those astronauts, they could put their thumb up, and they could wave goodbye, basically dismiss every human being that ever was, ever would be, and was at the time. And they all came in. They realised that we had to look after planet Earth, spaceship Earth. They all used the word fragile to some Americans, but fragile to us in New Zealand. And they want to look after it. And even that goes on, even the International Space Station astronaut Chris Hadfield, from playing David Bowie in the International Space Station, when they came back to planet Earth, they felt so protective of planet Earth, spaceship Earth, we'd even pick up litter because they didn't want us to. So we're starting to see this photo, Earthrise, it's got a name, taken by Bill Anders. It's perhaps the most influential environmental photograph ever taken, and that's not my words. And I would tend to agree because they kicked off the environmental movement, certainly around the world and certainly here in New Zealand and Save Manapuri, which is just up the road from here, which would have been wrecked otherwise if it wasn't for environmental movement. Anyone recognise this? Oh, okay. Yeah. That's Saturn, but I want to just mistake it's a total eclipse of Saturn taken by Cassini in 1990. I just wonder, there's a little dot there I just want to draw your attention to. That's not a pixel error. Can we see it? That's me waving. Standing there for the camera in 1990. And what that tells us is that if we make a wreck of planet Earth, there is actually nowhere else to go, right? But everyone of us here, the only time we're probably going to leave planet Earth is when, about 4 billion years' time, when the sun blows up and take us with it, like we stardust for the 4th time. But in the meantime, we better do something or other about looking after planet Earth. And yeah. Hey, actually, I'm not a nutter on this because I've been showing these slides. I made a point of showing these 3 slides every time, goodness knows how many years. I went to a conference in Pasadena 2014, and here was this joker, Gerhard Tyler, who was the payload mission specialist on Expedition 99 on the shuttle, showing exactly the same slide, the same reason. I thought, well, he's a smarter cookie than I am. It's good enough for him to tell this message and start every one of his talks with that. I'm going to continue. So that is the message from the sponsor. Look after Spaceship Earth because there is nowhere else to go. And space might be important in this. The COP21 measures, and I know the subsequent ones, you can only measure them from space. Well, half of them. Half of them can only be measured from space. So we need space to look after planet Earth. And if you want to feel a bit grim about this, I'll just put you in a downer. There was a conference in Paris last year, and there's a chart there. It's not great, but basically it's telling us that looking at 13 missions since 1992, the sea has risen 110 millimetres overall. You can only measure this from satellites, right? There's 13 of them that's done that over time. So it's pretty grim, and so I think we need to improve our effort on looking at planet Earth, but it's feel a bit dismal. Anyway, let's see what we can do. Let's not give up. And I have got perhaps one bit of bright news in that chart. I'm pretty confident that it was written in Python because most of the space community, their go-to language is Python, and then when they want to get really fast, they go to C++. And some of the geeks use R, but actually most of them use Python. So it's a bright bit of news, I guess. So a little bit about me, really. So I was born in 1958, just a couple of weeks ahead of NASA being formed. So NASA and I go back a long way. And I was born before Yuri Gagarin, so I predate people in space in 1961, which was, I was too young to really notice. But I was aware vaguely of Bill Pickering. Everyone heard of Sir William Pickering? No, okay. So he was born in Wellington, and he became the first director of Jet Propulsion Laboratories Pasadena facility. He was called Mr. JPL, and so he actually headed, that was the part that did unmanned spaceflight for NASA, and so he was responsible for the first successful orbit by the United States, Explorer 1, which was 1958, but after Soviets, of course. And that was on a Jupiter-C rocket, Juno 1. He managed NASA's lunar and planetary flight projects in 1962, the first time the Americans went to Venus and Mars and carried on to Mars. And he's still held in high regard. So you could say that New Zealand has taken the United States to the moon, and he's still highly regarded over at JPL and at NASA in general, actually. You can always get a smile out of them when you mention his name. And just as a side there, I put this in because we all like computers one way or the other, but the first photograph that came back from Mariner when it landed on Mars wasn't the photos that we're used to today. It was actually a paint by numbers effort. And if you look at the right-hand side there, very carefully, those are just strips of paper with 3 digits on it, and they developed a colour coding, went out next door, bought a box of crowns and coloured it in. So you can see where we might have come from. 8K resolution, we've actually started on, I don't even know what you'd call that, paint by numbers, just inside. But for me, I was interested in space a bit personally way back when I was 5 years old. But living over the back fence in Papakura where I lived was a guy called Dr. Brian Egan, and he taught at the Auckland University's engineering school, which was at Ardmore, just out of Papakura. And he was really into radio and radio astronomy. And in 1963, he got a Erskine Fellowship over to Ann Arbor in Michigan, and to work on the radio telescope at Peach Mountain. And he got that going, but suddenly they realised they needed the radio frequency synthesizers. In the good old days, if you had a transmitter, you had to have a physical crystal, not the little ones on the computer, but a big chunky thing. And they realised the astronauts couldn't carry around a box full of crystals, so he developed a radio frequency synthesizer that went into Gemini. And he developed the radio systems for Gemini, and which was carried on into Apollo. And then the office decided they'd move. Well, NASA decided they wanted them down in Houston, and Brian's wife Jean said no, and they came back to Papakura. What's this got to do with me? Well, the little guy there in the front is my best friend, Alistair, and he was 5 years old, just like I was at the time. And of course, when you said, hey, what does your dad do? And Alistair said, well, he put satellites into space. You can imagine how much street credibility that had with the other kids around Papakura. And the answer was none, and we had to defend his honour. So was a little bit of biffo. So my first involvement in space really was more biffo than science. In fact, Brian was really helpful to me because he introduced me to amateur radio, and he also said, actually, I should go and do an engineering degree at the University of Canterbury. And I did that in 1975, 76. And just to give you an idea of how ancient I am, just to run a simple 13-line code, we used Fortran. It was a batch process on a Burroughs B6700, which then took an entire building to look after it and to house it. And just to run a little bit of code, you wrote it all out on some forms, and the card punch operators would turn them into whole 80-line cards. They would get run in the batch, and then the following day you'd get the paper with your cards and a rubber band inside, and you would see if you made a mistake. And you can see here I used 1 second of CPU time and 2 seconds of I/O time at $54 an hour back in 1976, 19 lines of code, and I got a few lines of output. So all I can say is thank goodness that you guys don't have to put up with that. I'm pleased I don't have to anymore. But the following year, while I was still at first year at engineering school, Voyager 2 got launched. You remember Voyager 2? Yeah, it was in the news just the other week because it's had a little hiccup in the software, and it's sort of been 3 degrees off, of course, work anymore, where you couldn't communicate to it. It would have eventually, but JPL got it back. So it was off to the Jovian system in 1979, Saturn 81, the Uranus system in 86, Neptune in 89, and currently it's interstellar space outside of the solar system. Now, I just want you to just put that to one side. Remember Voyager 2. Remember exactly what I've just told you there, because it's very important. Meanwhile, I was carried on as a good engineer, go mountain climbing, use ham radio top of Mount Cook and all sorts of things like that. And I had a pretty crazy life being an engineer, and we did a lot of fishing, interesting places where you could build antennas like down at Scott Basin, things like that, or go fishing up in the Equator and sort of build telecommunications systems up there for the part of the United Nations I was working for, and build satellite ground station antennas that sort of had to go together in a pretty hard Armstrong way to do things and provide telephone systems to coral atolls in the middle of nowhere. And so I lived a few years up in Tokelau in Samoa, and I can recommend it. Good days are fantastically good. 10 years later, I'd found my way back, because you might be wondering why someone with all this is in Invercargill. It's a lifestyle choice. It's a fantastic place to live down here, I can assure you. You've got more mountains. You see, I like mountains and hunting and fishing and outdoors than you might care to think. But anyway, I'd returned to Southland, and I was doing telecommunications. And 2008, New Zealand went to space. Now, this is not a date that's really written up in any of the history books. It's a bit too near, I guess, and I don't think anyone recognises what happened. But 2008, I maintain, was a pretty seminal year in space in New Zealand. We had Dr. Chris Hann at University of Canterbury start up his rocketry group, which was mainly looking at what we call guidance, navigation and control. That's the bit that controls the rocket. We don't like to use the word rocket too much for anything that takes a satellite, but this is okay. Setting rockets up is actually not all that straightforward. The centre of gravity is up high and the forces are at the bottom. And if you want to try it out sometime, take a pen, balance it on your finger and see if you can hit the ceiling. And those are the forces and centre of gravity. That's the problem you're solving. I'm sure you can do that, practice that at morning tea. So he set that group up. Professor Sergei Gurliev at the Auckland University of Technology set up a 12-metre antenna at Warkworth, and remember that. Actually, remember all of this because they're all important. And Pete Beck, who's heard of Pete Beck from Rocket Lab? Come on, must be a few. Yeah. So he's the CEO and founder of Rocket Lab. There's a book came out about him and a few of his customers, especially Vance the other month. Local lad done good, actually. His dad used to be one of the conservators at the museum here. And if you look around town, there's a lot of sculptures, and they're Pete's dad's artwork, a lot of them. So he started Rocket Lab back then with his A301. He announced that, and looking much younger there. And here in Invercargill, we built the Awarua Satellite Ground Station. On the third on the left is very much younger than me. This what work does to you. It makes you get old. And say, why here? What sense does that make? Well, the answer was that between 2008 and 2014, the European Space Agency had a thing called ATV, or Automated Transfer Vehicle. Think of that as a 20-ton cargo truck going to the International Space Station. So it's taking food, it's taking water, it's taking air, science experiments, clothes. You've got to be an astronaut. You need all that stuff, right? Not just weightlessness and songs. And it went up, there's a picture there in the middle on the right-hand side of ATV. You put a London double-decker bus in it, right? And before we move on to the next slide, just notice those solar panels sticking out the back from the service module. Just remember that shape. Just mix all the other things I've told you to remember. And the reason they needed us was they launched from Kourou in yellow there, and in the sort of ballistic phase, as they call it, went over the back of Invercargill here, and they have separation. So you have the launch vehicle, so it's the rocket and the things, all the flames pouring out the back, and you've got ATV sitting on the front. And that's the payload. And they've got to separate somewhere. You don't send a whole rocket to the International Space Station. And they needed someone to see where the separation was, and they needed a downrange station here. Well, they'd done their homework because back in 1953, Captain Haddock and Tintin had already found Awarua. So they knew where to look, and they knew to find us. And they turned up a whole bunch of engineers and lawyers and head of international relations, came to New Zealand, and they found us, and eventually, and said, well, can we sort this out? They were very surprised to know that anyone in Invercargill would know what an antenna was, let alone what a spacecraft was, let alone. Yeah, but anyway, we weren't quite as good as perhaps they thought, because they said, oh, well, can you do it on radio noise measurements? We go, yeah, of course we can. And I had to go back to my amateur radio days, and I had to make the family eat a few cans of baked beans so I could make an antenna, and we could do the noise testing. And that's the antenna there on the right, and a much younger me. And the answer was, what do you put in the report? I didn't want to say baked bean cans. So I said, well, the Watties antenna with the 26 dB return loss got these measurements. And they were happy with the Watties antenna. I did show them, and they loved it, but that was sometime after. So what we did a real greenfields manoeuvre. So we started off with, obviously, for a green field. We're fantastic here in the south, and you would have noticed how green the place is. It gets pretty much the same amount of greenness in the middle of summer. It's not like Canterbury or somewhere horrible like that, or Auckland. We have green grass all year round. So green fields, that's where the place. And we finished off with buildings and things, as you can see on the right. It took about 4 years to get that far, tonight in 2008, to be fair. So that's why we're here. I'm going to come back to that, but who is the international space community we've been talking about, and how this might relate to you? Let's have a wee think. So I've got a friend in Virgin Orbit, and he and I have come up with some numbers, and these numbers are off the internet, so they're obviously correct. I'm not sure where on the internet, because they haven't posted them yet, but they'll be there. So about 20% under the launch vehicle. That's Pete Beck, that's a variety of other people. That's Elon Musk with his Falcon 9, Ariane Space with the ES. Basically, they don't care too much who they're taking into space. Well, they care a bit because they don't want a nuclear warhead or something that explodes at the top, because that becomes embarrassing. So we make the distinction between launchers and rockets. We're involved with launchers because they've got peaceful purposes at the top. So that's 20%. They don't really care too much what the payload is. They want the noise and the rumble and the flames out the back. Another 30% is the spacecraft itself, the bit that sits on top of the launch vehicle, and they don't really care who they go to space with. If there's a Falcon 9 available, they'll be on that. If there's an Electron, they'll ride that, and if there's an ES or something else and it's good enough, going in the right place, they'll take it. So they don't really care too much how they get to space. That leaves another 50%, and that's the payload data. They don't care if there's a spacecraft there or not. They just want to know that the internet gets them the data somehow or other, and they certainly can't care less how they manage to get the spacecraft into space in the first place. So I'm guessing that's, you guys sort of fit mainly into the grey area there. So that's pretty much C Python programmers, R programmers, pretty much. Yeah, might be a few other people doing Fortran still, but that's you guys. And then there's a little bit on the bottom which everyone forgets about. It's the ground segment, which is 0.0001% of the space community. No one's interested in the Cinderella of the space industry until they go to launch, because if you haven't got something on the ground pointing at the satellite, you might as well have a flying brick. And there are a few bricks up in space right at the moment. They're a bit bigger and they look a bit fancier, but they've got all the other characteristics of a brick. So suddenly we can become very, very important. And that's the bit that we do. And I'm going to just talk a bit about, wow, that's a bit esoteric. So let's have a look at one. So many of you will have a ground station at home, right? So you've got an antenna, you've got a set-top box, which is a decoder, demodulator, down converter tied into it, and payload data. And of course, the best payload if you're on Sky TV is, I don't know if it's there still, but The Dish. Everyone's seen the movie The Dish? Yeah, here's a few, good on you. Starring Sam Neill, the famous Australian actor from Wales. And it's got a vineyard up the road too. It makes quite good wine, I can promise you. It's all about the Apollo landings. I diverged, but it's worth seeing. If you're bored, you really should go and see it. And you can have a really simple antenna. It's bolted to your roof because it's talking to a geostationary satellite, which goes around, if you're 36,000 kilometres above the equator, well, actually 36,000 kilometres above the Earth, orbital dynamics say you will go around the Earth once a day, no question, no exceptions, well, almost. And so if you're ever going around the equator the same direction that we go around the Earth, it's going to seem fixed in the sky, right? Seems pretty simple. That's geostationary. Really simple. So we're a little bit more complicated because our antennas, our satellites we look at are much lower. And so we have to have a fancy antenna that moves around and needs a bit more gain because it's not beaming down with much power. And the satellites that we look at down at Awarua are only about 400 to 800 kilometres high, which means they go around the Earth in about 1.5 hours. We only see one of these satellites go over. It takes about 8 minutes at the most. So if you're out on a dark night and you see a satellite come over, it's going to be in low Earth orbit. It won't be one of the geostationary ones. And you time it and you can work out it's, if you can get a few calculations, but you guys are Python programmers, you can deal to that. There's plenty of libraries that you can download and do that. So I won't tell you how to suck eggs, but yeah, they're only 400 to 800 kilometres up. We need a slightly fancier set-top box, a bit more electronics, and for this mission, that's a launch, we need everything duplicated, and the payload, yeah, it's not quite as exciting as Sam Neill. It's looks a bit like that, but let's not go there any further. So that's our business of what we only do down at Awarua. And the stuff that might be in the payload data could be anything up the top there from Planet Labs, which you'll probably sort of see things like that on Google Earth, because they do provide stuff for Google. Could be what's over there on the right-hand side, which is a synthetic aperture radar image. That's looking at the Renner, and so that's looking through the clouds. Optical satellites can only look at what's, through, if there's no clouds there. We might have Starlink, we might have something to do with Apple, I don't know, or might we, and SOS system, and there's all sorts of other things. I mean, some really cool stuff. Some of our customers look at GPS satellites as they go over the horizon, and they, you can measure as the perturbations to the signal comes through on the receiver, you can actually work out what the atmosphere is doing, which direction the wind's going, how much moisture and how much bad weather. So that's Spire Global do that. So there's a lot of things that we do from space. And as I said, when you were listening to me, we've got only half of the COP21 measurements can be done from space. So sea level rise, measuring the density of the Earth or the gravitational pull, because you can't, that's the only way you can measure how much ice is melting away underneath the glaciers out to sea, because you can't measure from the top, but you can measure microgravity. So that's what we do. We look at Earth observation. Everyone knows the world's not round, it's not a sphere. We've told so often in the media that it's flat. So for the flat earthers amongst us, this is how we view the world. We're great believers in the flat Earth. And you could see that there's only a limited range of how far you can see, which it's hard to explain for flat Earth, but I'm sure it's easier for a spherical Earth. but for a lot of the spacecraft, they go over the poles, right? And so the closer you are to the South Pole or the North Pole, the better. The North Pole is full of ground station, Poker Flats, Svalbard, you name it, they're all there. Down here, we're as far south as you can get, apart from Punta Arenas, and we've still got the internet, and we've got REANs. And so you can see that we've got a fantastic location here for tracking low Earth orbit satellites down here at Awarua. In fact, we've taken advantage of that, and we've been building out. This is a fairly old photo. It's from March 2022. There's a lot more activity going on down there right now. But if you get bored, drive down to Bluff and turn left at the fertilizer works, and you'll eventually get there. And so we do two parts. So we host other people's antennas. These things are quite expensive, right? Like anything from $500,000 to a couple of $1 million. Those ones there, the big ones, are about $1 million mark. So we host other people's where if they've got enough satellites of their own, like Planet Lab, say 200 spacecraft, it's worthwhile them having their own antennas sprinkled around the world. And the other ones, maybe they go to a network provider who owns satellite antennas sprinkled around the world. Planet Lab came to us in 2013, introduced by Pete Beck, and they wanted a ground station. And it's sort of funny how the world goes, because they were trying to decide, because in the space community, the world's not very big. And as I say, you go around in an hour and a half. And were they going to build a ground station in Awarua, or were they going to build a ground station up in Newfoundland? And big decision, because they were still starting off in those days. They were pretty small then. And they're based in San Francisco, went down to the waterfront, Fisherman's Wharf, for their directors meeting, make the big decision, who goes past but Team New Zealand. And they go, hey, that's pretty cool. So thank you, Team New Zealand. Not that you know that you've helped us, but you did. And you see on the right there, that's their first antenna. It's in a radome. It's a bit on the outside is just to keep the weather out. There's a pretty picture on it, puts some frighteners into all the engineers, because no one draws pretty pictures on your radome, because it might affect the radio frequency characteristics. But hey, they're from California, and they have an in-house artist or residents. And so, they're allowed to do it. And we did the testing. In 2018, we were able to repay the favour from Rocket Lab, and they did their first successful orbital launch. And which was still testing, was the name of the launch vehicle. And I remember talking to Pete in Utah in a conference shortly afterwards, and said, "Oh, Robin, you're in the big time now with the in the space, with dealing with us." I said, "Pete, the last time we did a launch, it wasn't a little 300 kilogram Electron class. It was an Ariane ES, which was the biggest thing in production at the time. You had two customers, which was Planet and Spy Global. We had three, because we had you as well." So that's the only time I've ever had a chance to get one up on Pete, and probably the only chance, because he is an incredibly smart guy, and he can think at least two steps ahead of anyone else. So we build antennas down at Awarua. We do the foundations. There's a lot of concrete, and you might think, what's electrical engineering and got to do with concrete? But the point is, you need concrete. You've got to put the antennas together. You can see some being put together there. There's quite a bit involved in that, to be honest. And we're probably going to put 6 in over the next few months. So pays a visit. Radio spectrum management. This is actually something rather that we don't notice in New Zealand. Radios just work, and they need Wi-Fi. Well, you get a bit of, sometimes they clash and cause a little bit of grief because people are on the same channel. That is peanuts compared to trying to deal with space. That's all I'm going to say. And if you ever want to launch, talk to me 2 years at least before you want to go to orbit. Otherwise, you won't get a radio license. But we branched out. So hosting other people's antennas is one way to make money, but you can make an awful lot more if you've got your own antennas. And so we thought we could try that. How hard can it be to make an antenna, right? So we were part of Venture Southland when we started, which was the local regional development agency. We're now, we then turned into Great South, which I think provides some of the collateral and marketing bags today. And then we got spun off 2 years ago as Space Operations New Zealand, but we're fully owned by Great South and ultimately the local councils, Invercargill City Council, Southland District Council, Gore District Council, and also Environment Southland. So when we were part of Great South, all our profits went over to other areas, and so we didn't have an awful lot of money to reinvest in the business. So AliExpress to the rescue, where you can actually get 3.7 metre diameter antennas for a few $1,000s on AliExpress, free shipping to you, Kiwi. And on top of an old weather radar positioner, and that was great, except actually these things are a little bit more tricky than you might think. And fortunately, I've got a couple of research students from the University of Canterbury who helped us get us through that, to be honest. And we were wondering what to do, and then suddenly we had a customer in Michigan. He said, "We really need your antenna," and they put the pressure on us, and that meant we could put a fair bit of effort into the antenna and get it built and spend some money. If anyone wants to build an antenna, talk to me afterwards. It's not quite as straightforward as you might think. And you know the famous, we go to the moon speech from President Kennedy. We go there not because it is easy, but because it is hard. We've got a slightly different motto. We go there not because it's easy, but because we thought it should have been easy. Anyway, once you know it, then that's, suffering's a good way to make sure that the lessons remain. A thing that we're also really lucky here in Southland is that this is off the internet, so I can show it. We pick up Pete Beck's Rocket Lab launches going to the South Pole T+2 minutes. So 2 minutes after launch, we get visibility of his launch vehicle. It goes around the world. It's a bit hard to see on that, but 3/4 of an hour later, it's going over the back of Ireland. They do separation there, and then they come back over basically a whole lot of ocean, and it's not till 110 minutes, 10 plus 110 minutes, we see them again from here. And so we're quite an important down station to know that actually separation went well. All the spacecraft that he was taking into orbit actually went into the right orbit, and things are all on track, which is good, because otherwise there's a lot of talking on the phone to the insurance companies. We see that as a lot of our Python coding and engineers are looking at how do we, at Space Operations New Zealand, we're looking at how do we identify that first path, because it's not too straightforward. Even with radar, you think, the ground-based radars can look at the satellites and work out. But if you've, say, on a Falcon 9 and there's 40 spacecraft just got ejected at the various bus stops on the orbit, on the launch, that's fine, but which of those is mine? And if I've got a high-gain antenna, do I point it here or here to that one, or which one? We think we've got that problem solved, and we're in the process of implementing that now. And there's a talk later this afternoon that will explain that, I think, I'm hoping, Chris, in a lot more detail. We do quite a lot of R&D, mainly because we can't afford to do some of the things that we would like to do. We're small, right? We are quite small. I mean, my colleagues in Deutsche Luftfahrt and over Pfaffenhofen, they say, well, yeah, we get a problem. So the way we solve a problem is we get a little team together of about 12 or 14 engineers, and we write up specifications for the code, and then we submit it to the coding department, and 3 months later we get all the code and we run it. Basically, that's one person's job here to do all of that. So I don't pay them 13 times as much money as one programmer, but yeah. So we have to develop the hardware ourselves, and you can see some hardware and testing and pre-drawn design that we're doing ourselves. And it's quite a good way, because the little bit about radio frequency engineering that we know and positioning antennas and building antennas turns out to be a lot more than most of our customers, in fact, nearly all of our customers. And we've developed that in-house down here. And so we've got I think we've actually got some genuine expertise. And people, when you have, I better not mention their names, but when you have some companies with names that you'd be familiar with in the space business asking us for advice, you sort of think, yep, that's better than the other way around. We also do, in the space operations itself, we were involved and assisted the University of Auckland with the APSS-1 satellite that they tried to launch a few years back, just before COVID. You can see the APSS-1 there. That's the engineering model. There's two pictures of it. It's a CubeSat, so it's 100 millimeters by 100 millimeters by 100 millimeters. That's a standard small satellite unit these days. Universities often do a 1U More important guys do 3, and they've got tons of money to build a 6 unit. And if you're going to the moon, maybe a 12 or a 24 unit, but they've got a lot more money. And you can get one of these to launch, depending on who you launch with, and who pays for putting all the integration and the parts for the satellite together, somewhere between $500,000 and $1 million for a 1U CubeSat, which is, okay, that's more than my wife would let me spend, but it's not unaffordable, right? APSS-1, that was a student mission. Unfortunately, it took a bit longer for that to get built and qualified, and the students all graduated, and Auckland asked if we could reverse engineer it and qualify it for launch on the radio side. The engineering model is, you always build 2 spacecraft at once, right? You have the flight model and the engineering model. You test and do all the experimenting on the engineering model, and then the implementations go onto the flight model. And then when it comes to launch, you send off the flight model for aggregation and put on the stack. And you've got the engineering model doing the other debugging afterwards. If you lose the flight model on the way to the launch aggregation facility, then you suddenly put some solar panels on the engineering model and send that off instead. Unfortunately, that there was a problem with ejection, and so we spent 3 nights and 3 days busy trying to find it. We would have found it, but unfortunately we never were able to make contact. There was another APSS-2, I was talking to Jim Hickey the other day, and they will be hopefully launching end of next year, APSS-2, and we'll be assisting them again. We also helped the University of Canterbury with their rocketry. Everyone will be familiar with White Zones testing grounds. States, yeah, probably not so familiar with the Waikaia rocket testing grounds in North Canterbury and a Piano Flat. Yeah, it looks a bit like a shig paddock, I guess. So we assist Chris Han with his rocketry launches. These are not going into orbit, right? They're only going between a few kilometres, and there is one launch we're looking at to 100 kilometres to the edge of space and the start of space, the Carmen mine. What he's interested in is slosh. When microgravity does horrible things, it's really hard to understand. Space and zero gravity does not do things that you would expect. Heat does not rise. If you've got a semiconductor or a microprocessor and you expect that the heat just to dissipate off like it does, in the back of your laptop without a heat pipe, of course, it's not going to work. In fact, the heat pipe's not going to work either unless you've got a fan blowing air out. No reason for lighter things to rise above the denser, colder air. So all sorts of weird things. Our gassing, your components can actually blow up because they've got bits of air inside the construction, and then it goes into zero, really hard vacuum. They're probably going to blow up. There's all sorts of things that go wrong. So this small rocketry is actually really critical, but the most important part was from Chris's work was the guidance, navigation and control system of pointing the spacecraft, the launch vehicle, and ensure it went exactly the right place. Chris's postgraduate students all went off initially to Rocket Lab, and they have a reputation for being one of the most accurate launch services around, which is really cool. And we still collaborate with the University of Canterbury. I've got 2 postgrad students full-time working for me because their research is aligned with what I want to do, and we've also support their undergraduates. Another exciting thing that some of you may or may not have picked up beginning of the year, we're involved with Lockheed Martin, the Southland project. We're putting, basically, this is the ultra accurate GPS, it's not just GPS, and global navigation satellite system. So if you've got a Garmin GPS, an older one, it might say, yeah, you've got 3 meter accuracy. The chances are, if the ionosphere, it's not a big chance, but it's a really, really low chance, but if the ionosphere, the atmosphere and the troposphere are all having a bad day, the radio waves from the GPS satellite, instead of coming directly to your straight line to your handheld, might take the scenic route. You could be 100 meters out, which is probably a bit tricky if you've got a driverless car. They would have you in someone's front lawn, I would suggest, probably out the back lawn. So we were involved in some really work with Geoscience Australia and Frontier SI to put a business case together where what you do is you have a whole lot of monuments, like on the left-hand side there, tied up to a little atomic clock or something, sprinkled around Australia and New Zealand. And so you know where they are. By over time, you're averaging all the positions of where you think. But you could, any one given time, you can see that there's a variation. That all goes back to a big computer. The computer builds a model for what the variations are around Australia and New Zealand, beams it up to encodes the correction, sends it up as a signal to a geostationary satellite, and then when your GPS handheld, all the GPS satellites coming down, to triangulate where you are, but also this is error correction. What that means is that you should be, with your iPhone or anything, you should be within 10 centimetre accuracy. This is in Europe now. We're building this right at the moment down Awarua. There's some really big 11-metre antennas, so put that into perspective, that's 20 concrete trucks worth of concrete for each foundation. So that's coming soon to be reliable. It sort of works off and on now, but you can't be sure quite when. All our customers are overseas. We don't get a choice on that. Probably less than 2% of our customers would be in New Zealand. So we have to. COVID's a bit tricky. Actually, it was quite nice. We didn't have to travel so much, but we have to go to the shows and things and meet overseas. But we do actually do a lot of our marketing is actually by word of mouth. Being based in the bottom of New Zealand is not actually all that big a deal. If we're going to be in New Zealand, actually Invercargill is no worse than being, it's another 3 hours on a plane or 2 hours on a plane by the time we back around. Than if we were based in Auckland and things. We don't have the traffic, so it's actually faster to get to the airport. By about 3 hours, 12 minutes to the airport, everyone notice? Yeah. I live on the edge of town, 12 minutes to the airport, another 15 minutes, just get there just before the plane goes. We do a lot of education, work with the German Space Centre. Interesting for the programmers, all their software is written in English. And you might think, even the name of the German Operations Centre, GSOC, Space Operations Centre, is G. It's not D for Deutschland. And that's because the universal language in science is English. Yeah, probably Russian, but it's not so international anymore. And so, because they've got people from all over Europe working there because of the EU rules and Schengen, and so, but we sneak in the New Zealander in that picture there. Might hear from him this afternoon. So we put training. We encourage the universities to work with us. We reach out to the local schools. We don't have a research university here in Southland, and so we've done our best. And with the European Space Agency, one stage we were working under quite a nice agreement I came up with. And top middle right there is Roberto Vittoria, a really cool dude. Used to be Italian jet fighter pilot, a test pilot before he became a NASA astronaut, flew shuttle. He suddenly went on Soyuz, became fluent starting from zero in Russian in 3 months. These guys have got some brains, right? And he went to I took him to the local Southland Girls High School, and he lost his voice, so I had to give a really boring Swiss head of the Vega launch program tutorial instead, and his slideshow doesn't look like a telephone book, right? But the girls were entranced, and once I started arguing about some of the telephone numbers. We got, over 5 years, we doubled the number of kids completing year 13 physics in Invercargill when we were really putting effort into the rest of the country was declined. We doubled. And 1 year I felt very proud of, and it wasn't all to do with us, our work, but there were 5 young women all graduated with engineering degrees from the University of Canterbury, all from Southland Girls High School. So these things can be done, and I think those are the things that we exciting our kids and getting them really wanting to do cool things, and it's never too early to get them excited into space, which is why it's always inconvenient, but it's always fun to host schools and kids, and we have quite a strong public outreach. More recently, things have got exciting again. Excuse me. I sort of joked to my colleagues in JPL and NASA, hey, we're taking NASA back to the moon. So you might be aware of the Capstone mission in 2022, which was launched. That's not actually, that's a daytime launch, but it was on an Electron launch vehicle. And they went to the Lagrange point. There's a position between the moon and the Earth, which where the pull of the Earth and the moon are equals, and so you can put the in theory, it was you can have the lunar gateway. We can have astronauts making expeditions to the lunar surface, and also as a staging point to Mars. And Capstone was the first of the Artemis missions to go and prove that this was possible, and to prove that that you could actually be in what's called a halo orbit. It was actually going to work. And so we were really excited for Pete when that was an incredibly successful mission. They had a few little problems on Capstone itself. That's the spacecraft. So we sort of say, yeah, it was really nice for me to say, yep, not only we Bill Pickering in New Zealand get NASA to the moon in the first place, but we're getting you back there again. And a little bit to do with that, we're going to have some real skin in the game. In July, Auckland University of Technology decided no longer wanted to do radio astronomy. And so we took over their 12-metre antenna. 12 metres is quite big if you think about it. And we also got a 26 years use of Spark's 30-metre antenna there in the background. 30 metres diameter, guys, that's pretty big, right? And we will be upgrading that, not just for doing radio astronomy, all things on the universe, everything that's above absolute zero gives off radio waves, right? And we'll be using that to support Moon and Mars missions. There's Artemis down on the bottom left there, and just look at those solar panels. Remember I said look at the solar panels from ATV, same thing. So the front bit, which is the pointy bit with the 4 astronauts inside, out the back is the European Service Module, and that's got heritage back to ATV. So we think, we've got a bit of, we were there. We'll be using the Walkworth antenna for mapping the spiral arm of the Milky Way. Who knew that there was a south spiral arm of the Milky Way in the first place, but there is, and we'll be carry on doing that. The VLBI, very long baseline interferometry. I'm not going to bore you, but basically with the 12-metre antenna, we now look at a whole lot of radio sources at this edge of the universe, quasars, and we can find out from that with a whole lot of other stations in Tasmania and Singapore and Honolulu, other places, we can work out where New Zealand is by triangulation to 2 millimetres, which is pretty cool because the North Pole sloshes around because there's a lot of iron, molten iron underneath us, right? So the North Pole that we rotate around in any given month might be 10 metres. We have to measure this all the time. That's New Zealand's contribution. We also got an atomic clock, so we can tell the time at Walkworth with a hydrogen maser clock. So give you an idea of that. If it was switched on when humans first started roaming the planet, it would still be within a couple of seconds, right? But that lets us do ranging. We can work out how far away the radio signals take to get to distant spacecraft and back, and we can measure it. Remember Voyager 2? I talked about Voyager 2. I said don't forget. So here's the Neil Archie, actually Charles Archie Mission Centre in Pasadena. It's called the Centre of the Universe. There's a little tile in the middle of the floor there. It says, this is the centre of the universe. It's the centre of the universe because all the deep space missions data all comes through this room and controlled by one of these consoles here when it's in operation. And there's a little joke there. JPL guys have got a good sense of humour. Basically, if you can prove that's not the centre of the universe, you can have a Nobel Prize. So here we are, board. So we'll be supporting, all going well when we're finished qualifying our 30-metre antenna, hopefully New Horizons, which did the Pluto flyby back in 2015, and we'll also be supporting Voyager 2 alongside Canberra. So that's pretty exciting. We're pretty chuffed about that. We've got a few things just to prove that the antennas and radio system is going to work. That's been done right as I speak. So let's see how that goes. Invercargill here, we are slowly becoming a hub of space technology, as well as us down here. We've got Lockheed Martin. They've got staff down here in Invercargill now. Actually, not quite true. They've got an office, and their first staff member turns up on Monday. We'll make them feel part of the family, don't worry. And we've got Global Star here. So these might be the guys that when you do your iPhone 14 and iPhone 15, you set off the SOS button in the back of nowhere, sends a signal to the satellite, and the helicopter comes, SAR Rescue comes and rescues you. Yeah, okay. I won't say any more on that. We've also got a whole lot of customers who come out here all the time from Norway, from various parts of the US, from Italy. I mean, it's not huge, you could argue. I mean, 29 bed nights in May, was a quick calculation I did, but that still adds to the number of people we have here. So it does help, and it's quite nice to have something high-tech that we can work to. So we're 100% waitlist. Nearly all of our customers are overseas. We're profitable. We've got year-on-year growth. And problem we really have is the opportunities we have really outstrip capacity that we've got, and we've got a few engineers starting over the next few months, but really I could do with a bit more money and a few more engineers and a few more supports. So who would have thought they were doing all this from Southland? None of you, obviously. I'm definitely not. And maybe it's a little bit kept secret, but the trick is that if you can do something or other and make it work, then that's got so much more street credibility than saying this is what I'm going to do in the future and or what I want to do. And there's any number of dreamers and wannabes, but actually doing something or other and having street cred around the world actually doesn't always buy you credibility in New Zealand, but who cares? Anyway, thank you very much for listening to me. I think we've got some time. We've got some time for some questions if there are any. Otherwise, we can have morning tea. You have a choice. You can talk to me, we can have morning tea. No, here's a question over there.
For the questions, can I ask you to repeat the question once it's been asked? Over here.
Yes, yeah. Would you take the other extended activity? The thing that the part on it is.
So,
can you repeat the question? Sorry.
So the question was how excited is the Voyager team now into the other salt voids? So not just the Voyager team itself, but also JPL, Big Space Network guys. There was an acute shortage of large aperture antennas around the world. I mean, to build a new walkway with in the order of something between $50 and $100 million. And there are people, the European Space Agency and with the S-Track network and the ESC are building some more 30 metre size bath units, but they're just not enough. So put it into perspective, with the Artemis 1 launch last year, and there were 12 ride shares. So sometimes you hitch a ride and, you're not too fussy where you're going, you just go where the main payload goes and you go with it. There were 12 ride shares. Because they've been on the stack, they used them for 18 months while they got the whole stack, the SLS to work. Some of those missions had real problems with batteries, the switches, deployment. DSN just did not have enough antennas to, do we save Artemis or do we save the ride shares? And of course, all the guys at ride shares say, save us, save us. But Artemis, that's worth billions of dollars. So of course, that was the major one. It was nowhere near. It was a paper I heard in Paris in the last year. Basically, they're going to be 10 large aperture antennas down. The problem with the moon's the problem. Everyone's going to the moon. And when Neil Armstrong went to the moon, 3 antennas around the world was enough. Canberra, Madrid, and Goldstone. If one of them died, the antennas didn't work. Okay, it was a bit tricky. Go and watch the movie, The Dish, and you understand this a bit better. But there was the Blazing Frontiers, and they lost a few astronauts and stuff, right? Now it's different. The astronauts, you've got to look after them. NASA losing astronauts is a really bad look. They don't want to do that. They've lost too many already. But also, the astronauts are going to be a lunar gateway for perhaps weeks at a time. And they got on and said selfies and Facebook, and there's a whole protocol for deep space internet going out to the internet to Mars. It's all go at the moment. How do you deal with that with a 3-minute time lag or 8-minute time lag? Okay, you clearly not the technologies you're used to terrestrially. So there is a shortage of antennas. So basically, DSN again, fantastic. As soon as we finish the qualification, we want to start testing. The mission PIs for each, for Voyager 1, Voyager 2, and all the rest, they can't wait. And if we can take over moon missions as well, that frees up some of the 70-metre class antennas that JPL have got. So they can, if we look at the moon, support those missions, then they can look after the deep space missions. And on top of that, Voyager 2 and New Horizons, why they're so interested in those is because they are they're in a southern inclination, and so you need a southern incline. You need something in the southern hemisphere to look at them as opposed to the northern hemisphere. So the answer is I don't know if Sammy's talked to them yet directly, but certainly DSN are really excited, and I would think New Horizons and Voyager 2 PIs will be pretty excited when they find out. I don't quite know where that discussion's got to. Sorry, that was a long-winded answer, wasn't it? Radio waves often don't care about political borders, so that is a difficulty. So it's managed by the general rules are fought out every 5 years by the International Telecommunications Union, I sort of worked for once before. Yeah, and the cellular operators want to have all the spectrum that they can possibly have, which is, the radio astronomers saying, oh yeah, but that's some of ours, and I'm going, I want to transmit on these frequencies, and these cellular people with cell phones, that's a nuisance. At Awarua, we've through a whole lot of work over the last 10 years, we've got really good access to radio frequencies down there. But Warkworth, it's actually really problematic. So radio spectrum around the world is a really big problem. There's two other big problems. One is the knowing where you are in orbit, because if it collide, you're in real trouble. And so making sure people don't bang into each other, which could give the Kessler syndrome and wipe everything out. And then the third one to watch, and you've been watching, if you're listening to the news over the last few months, is the race to the South Pole. So it's not the South Pole down here, it's the South Pole on the moon. And if you look at the moon treaty, you can understand why. Anyway, I think I've got the marching orders, so thanks for your time.